moment that you find it in the archive. This is the result that we have. So if we detune from the resonance of the resonator, then we only have back reflection from the front mirror, and then we measure with this detector here, the direct reflection, we measure this shape. So then at early times, so we have this exponentially rising pulse that we create here. So the exponential tail comes first at early times, and then at later times it increases, and then there's this drop-off. Now, according to this time reversal symmetry argument, if we go on resonance, this time reverse, this exponentially rising pulse should go all into the resonator without any reflection until there is this cutoff. And then, for one moment in time, all this energy is inside the resonator, and then, of course, the resonator starts re-emitting. So what we expect is at the moment when there is this sharp falling trailing edge comes to the resonator, then and there's no more light on the input side, then the resonator will start emitting. And you see it's what we measure experimentally is very close to what we expect ideally. So this is not a step function, but there's a slight slope, but you can see it looks very close. So if we were further away from the ideal case, we would have more reflection here, so we would have an exponential, some direct reflected light would be an exponential rise here, and then maybe a slight jump, and then an exponential tail. So the balance between these two sides will tells us how well this works. And if all the intensities to the right at positive times here, that means we effectively had all the light inside the resonator. Okay. So this was the this was the introduction where we tried to convince ourselves that in other optics examples we can use time reversal symmetry, and now we want to apply this to the case of a single atom and a single ion. If we have an atom interacting in free space, interacting with the light field, we have all these different directions where the light can go to. We have a continuum of modes, and so the question is, do we have this case where we have all these degrees of freedom that we cannot control, or what is the situation? So the atom needs two levels, and then it will be interacting with the modes which are more or less resonant with the atom, but this is a reservoir of continuum of states. So in principle, the recipe would say we start with maybe in a Gedanken experiment with the excited atom, and look at what kind of photon wave is emitted by the atom. And then we should prepare the time reversed version of this, and that hopefully would bring the atom back to the excited state. But we need to understand what is the wave that is emitted from a single atom when it is in the excited state. So we know it will be radiating more or less in all directions, but how will it look in time? Now here we have the typical situation that you have when you do quantum measurements. You have a system that you measure, then you have a detector, and the measurement result that you will get depends on the question that you ask, on the type of detector that you use. So we will start out with a detector which is time resolving, and then we will switch to a detector which is spectrally resolving. So let's start with a time resolving detector. So we prepare the atom in the excited state at time 0, and we plot as a function of time what kind of signal we get from this detector. So if we do this experiment once, we will get one click. Of course, this has to be not only a time resolved detector, it also has to be sensitive to single quanta. So we will see an electronic signal typically, because this output will be an electronic signal, and the width of the signal basically is given by the bandwidth of the detector. So when we do this once, we don't know so much. We repeat this, and the histogram builds up, and eventually we will see there is an exponential decay. This tau is called the mean lifetime of the excited state, describing this spontaneous emission. But we can also do a different experiment. We can do a measurement in the frequency domain, and you know that time and frequency are conjugate variables. So let's see what we get there. So they are basically mutually exclusive. So if we, that means we cannot do both measurements without introducing noise or uncertainty at the same time. So we do the same experiment. Now this detector typically will be maybe a spectrometer with some, with a very sensitive camera at the output of the interferometer, of the spectrometer, maybe a grating spectrometer. And we will then again do this measurement, and we now plot at the output these different pixels of the camera correspond to different frequencies now. And we will see one of these pixels giving a signal. Then we repeat the experiment, we excite the atom again at time equals 0, or we excite the atom at time equals 0, we excite the atom again and let go, and then we will see another measurement result. Another pixel goes click, and again we build up a histogram, and now we have a Lorentzian, the width of which is proportional to the inverse of this mean lifetime. So now the question is, what is the photon wave packet which is emitted by the atom? If the width of these electronic signals that we see in the time resolved measurement, if this were the true, this would represent the photon in its temporal behavior, then the corresponding spectrum would be the Fourier transform of this, and would be much larger, even larger than I pointed out here, and definitely larger than what we see. So this is not the wave packet which is emitted, and the only consistent explanation is that the atom emits a photon wave packet which is given by this blue curve. And so when we were thinking about this and discussing with the students, we were thinking this word mean lifetime is not really a good word, because it indicates that some atoms live shorter and some live longer, and that's not really how one should look at this. The atom starts immediately emitting when it is excited, and it will emit this wave packet with this exponential shape. And only when you do a measurement, then of course the absolute squared wave function will give you the probability at a given time to see a signal. And so this stochastic element comes in through the measurement process and not through the interaction of the atom with the environment. So the interaction with the environment is a unitary process, and as such can be reversed in principle. So now we learned what we need to do. We know that the emitted photon is an exponentially, is a wave packet, it's a sharp rising leading edge and an exponential tail. Incidentally, very similar or the same as for the resonator, only in this case it's only a single photon, and the resonator can do this for many more photons. And what we need to provide the atom with to get 100% excitation is just a time reverse version. So instead of having an outgoing wave, we need an ingoing wave. Now, I did not discuss the spatial dimension, but I wanted to emphasize here that the mode of the spatial mode of the light field that the atom couples to is a dipole wave in the case when you have an electric dipole transition, which is the normal case. And that means that the atom couples only to one spatial mode, and then in this spatial mode you have this temporal evolution. So you have a problem which is kind of like one-dimensional in time, because you only have this one spatial mode, one dimension. Oh, yeah. So it's as if the atom would just be emitting in one spatial direction in one dimension. This is the geometry, of course, when we provide the single photon wave packet that should hopefully very efficiently couple to the atom. Then we need an ingoing dipole wave. This is part of time reversal. We have to get the polarization right because the fields are always vector fields. And the timing we discussed in detail. And the statistics, that means that we have to have a single photon, of course. If the outgoing wave packet, now this blue circles should indicate this spherical dipole wave. The dipole wave, of course, if it's a linear dipole, it has different amplitudes in different directions. I didn't show these details here, but it basically goes in more or less all directions. But it's a wave packet. The excitation is described by this sharp rising leading edge and exponential tail. So if we would now send this, so what we need is this time reverse pulse with the exponential tail coming in first. If we would just reflect the light beam, we said this before, so that the sharp rising edge will come in first, then the coupling efficiency will not, one can calculate this, it will not be 100%, it will at most be 54%, so you can never come close to 100%. Theory paper on that a while ago. So the experiment, how do we want to do this? How, for experimentally, so conceptually this is a very simple experiment, but in the lab this is not so simple because you have to have an atom, a two-level system, which is fixed in space somewhere. It's open to irradiation from all sides, and you actually also have to send light in essentially from all sides. So when you do experiments, you have to make a decision, or you have to make decisions again and again. And one decision we made is that we said we'll go for an ion that we trap in a Paul trap. Of course, for this you need electrodes. So one of my students a few years ago went to Lake Wineland in Boulder, Colorado, to develop an ion trap where all the electrodes are on one side, so that only a very small part of the solid angle is obscured. And now, how do we provide the light field that comes in from all directions? So the natural thing to use is a deep, very deep parabolic mirror. This is this here. So the parabolic mirror will provide focusing from a wide solid angle. The deeper the parabolic mirror, the larger this angle. In the best parabolic mirror that one can buy will still have some aberrations if it's such a deep mirror, so we have to measure the aberrations, we have to compensate for them, and so we have a correction plate at the front. And so on the one side of the plate there's this modulation of the surface that corrects aberration, and on the back side, so this is something that I thought we could do. My students tell me, why don't you take one step at a time? But in principle, in the future, one could even have a Fresnel lens imposed on the backside, so that part of the incoming light beam is also, so that one closes this solid angle, this opening. But even without this, it's not so bad, especially if you choose the atom that you want to excite properly. And in order to make the experiment simpler, means in order not to suffer too much from this opening here, the idea is to excite an atom in a linear dipole transition, with the linear dipole being lying along this direction. And the linear dipole, if it radiates in the equatorial plane and not in the direction where the charges are oscillating. So you have a cosine squared distribution, rotationally symmetric. And if you want to excite a linear dipole, you have to have the inverse. So if we want to excite a linear dipole which oscillates in this direction, we mainly have to send in light from this part, and this ring around here, but not so much from the front, and also not so much from the other side where we have these electrodes and we cannot provide light anyway. So with the experimental shadowing, and this is about 1-to-1 the dimensions of our parabolic mirror. This is a picture of the parabolic mirror, this is the Europoint. We cover like 94% of the dipole mode. We only cover 80% of the solid angle, but because of this weighting, because of this amplitude distribution of the dipole wave, we cover 94%. So in the experiment, we will not be able to do 100% excitation, at most these 94%, and maybe a few percent less. But if you want more, we can always close this gap. This was, so the 94% is without the Fresnel lens here. With the Fresnel lens, one would then go up to like 97% because we're still skewing here on the back. Okay, then you can ask the question, okay, suppose you do all this, how do you know that photon was absorbed? Because if you send a single photon in here, it will be converted from a collimated photon to an ingoing dipole wave carrying this one photon excitation. And so it will either not excite the atom, or it will excite the atom, but then the atom will re-radiate, and in any case the photon will come back out. So how do you know you will have had 100% absorption? And the detection is done by this delayed emission, similar to this. So first, if it's done properly, then first the energy will be stored in the atom, and then it will only radiate, like with the resonator, in the case of the resonator. And so you have a time delayed emission, and of course there is this inversion of shape. Just as these experimental figures that I showed you of the resonator. Now, this is a linear dipole transition, so we had to choose which ion we are using. So we want a two-level system, so we want only a single level in the ground state. So, for example, a J equal 0 to J equal 1 transition would do, J equal 1 being the excited state, it would be state, yeah. So it would be now, in this time reversal Gedanken experiment, if we start with the m equals 0 state and let this evolve, there's only this one decay channel, and so in time reversal, one would have to go back up. If we would invert J equal 0 and J equal 1, and if we then start with the J equal 0 the state here and let go, there will be these different decay channels. And of course the time reversal argument will still hold, but it will be so difficult that I don't know how to do this experiment with this particular scheme. And I want to show you why. The wave function after this emission, the wave function is a strongly entangled wave function, entangled between the polarization properties of the outgoing light field, sigma plus, pi, sigma minus polarization, and the magnetic quantum number of the remaining atom. And time reversal would mean that you prepare an atom in the ground state and a photon wave packet far outside, of course with the right temporal shape, but this is peanuts compared to this problem here, in such a way that it has this entanglement. So the only way to prepare such an entanglement is in the emission process itself. So you could say, why don't you just use the spontaneously emitted photon, which decays in all these different channels and